So, this lecture is Open Ocean 2. Now, here I will discuss mainly of first one is your Coriolis force, or this is called the Coriolis effect. Now, in your mechanics class you must have come across this word Coriolis. This is because of the Coriolis means what? Because of rotation of the earth. So, this is another cause for your current, rotation of earth. But you have to know the mechanics. Now, here actually you will find the earth is having a spin. So, my diagrams are not perfectly round. Say this is your north pole, south pole. So, this is your spin. Now, because of this spin, you will find that you are having two radii. Say theta is this angle. Say how much is this distance? So, this is r cos theta. So, now you find out the angular velocity. Now, r is equals to how much? Is 6378 kilometers at equator. What is the value of your radius at theta equal to 30 degree? Say as an example, let us take the value of this theta, say theta equals to 30 degrees. So, 30 degree latitude. So, radius is r cos theta. So, this is 6378 and cos 30 degree find out. So, this is 0.866. So, this gives us 5524. So, radius is shorter by how much? So, more than 700 kilometers. So, find out the speed. Speed eastward. Of a particle at equator. So, how much is that? This will be circumferential speed is 2 pi r divided by 24. So, at equator your rotating at this speed, which of course you don't feel. So, this is 2 pi multiplied by 6378 divided by 24. This works out at a tremendous speed of 1669.8 kilometers per hour. So, this is what God is doing to you, which you are not able to realize sitting in the classroom, isn't it? Now, what is the speed? To find out first speed eastward of a particle at 30 degrees latitude, or rather you write at 30 degrees north latitude. So, this is 2 pi multiplied by r cos theta. This is your spinning speed divided by 24. So, this works out to be how much? This is 24, 6378 cos 30 degree multiplied divided by 24. This is 1446. 1446 kilometers per hour. So, this is at 30 degrees latitude. So, that means how much is the loss in speed? So, there is a loss of speed. So, this is 1669.8 minus 1446. This is equals to 223.8 kilometers per hour. So, that means a person who is at the 30 degrees north latitude. So, you see a particle going towards the right at 223.8 kilometers per hour. If you consider the 30 degree latitude to be stationary, you see a particle fly past like this towards the right. So, that is what is happening. Now, that explains this direction of the ocean current. So, if you see the direction of the ocean current to the north of the equator, best is if you throw a stone from the equator, which direction it will go? It will go towards the right, isn't it? So, that is the clockwise movement of the current is taking place because of the Coriolis force. Similarly, if you throw a particle from the equator, it will go towards your left. So, that is your anticlockwise spin. That is a subtropical Gaia. So, this is the gives an explanation to the direction of the current. So, this is called apparent deflection. Of a moving particle. Apparent deflection of a moving particle to this, you should always remember, to the right. this occurs in the northern hemisphere. And apparent deflection to the left. In southern hemisphere. So this is your Coriolis effect. Now if you want to study this in detail, now this actually deflects, is a cause of deflection for both. Cause of deflection for number one you write winds, and number two you write ocean currents. So that is why the Coriolis force is important, and especially this is affecting, in this diagram you can see it is affecting near the equator. The equatorial region is most affected by your Coriolis force in this diagram, because the speed near the equator is larger. Now the last is your what is called the Ekman spiral. Now this is caused by wind. So major cause of the Ekman spiral, I will explain what is this Ekman spiral is, but this main cause is the wind. Now this wind blowing over the ocean, this actually sets water in motion. Now, if you read the mechanics, there is a cause of wind stress. Wind actually causes a certain shear stress on the water surface. So your water surface forms layers. These layers move against each other. So that is called a shear stress caused by wind. Cause of wind, or rather you write shear stress in water. This is caused by dragging effect. Dragging effect on surface waters. So the wind actually somewhat sticks to the water and it drags the layers of water. So there is a frictional force causes ripples, RIPPLES. Now, ripples are named as surface roughness. So, whenever you see ripples, you will find there is a light breeze blowing, which is causing the water to slide against each other. Now, 12-hour steady wind. Steady wind at 100 centimeters. This is 100 centimeters per second. Normally causes ocean currents. Or rather ocean surface currents. At 2 centimeters per second. So, this is roughly 2% of wind speed. 2% wind speed. So, this is the cause of ocean surface current. This is an example. And the depth of influence of this wind driven current is this. So, water current due to wind extends at least 100 meters below surface. Now, here this is a diagram of water movement. Now, this occurs in the northern hemisphere, or rather you write in a wind generated. Wind generated current in northern hemisphere. Now, why I am writing northern hemisphere is by looking at this diagram you can tell me. Now, if you take a vectorial spread, let us say that your wind is blowing in this direction, then surface currents will go like this. Now, if you go deeper down into the water, what will happen to this current? That is, the current vector will gradually decrease. Now, the vectors will get reduced in length, but also it will change the direction. You can see like this. As you go deeper down into the ocean, the current vector actually diminishes in size. Now, you go on down below, and after a certain depth, say 100 meters, that is the influence of the wind, you will literally find the direction of current is opposite to your surface current. Like this. Now, if you join these ends, you will find that you are getting a sort of spiral. You take the projection of these vectors on a piece of paper, you will find you will get a curve like this. So, these are the projections. This will all come from this point. So, this is called a Ekman spiral. Now, if you draw the surface wind pattern, you will find that the direction of the wind is in this direction. Now, surface currents you get 45 degrees to the direction of the wind. So, this is your wind direction, and this one is the direction of surface current. Now, in most cases it will be 45 degrees, but this angle varies. So, in actual sea, angle varies between from 15 degrees. In shallow coastal waters. Why? To 45 degrees in deep waters. So, in shallow coastal waters, it gets affected by bottom friction. So, you have less, that means the frictional force is higher. So, that means you have a lesser angle. Where friction is, bottom friction is not there, then it is 45 degrees. In deep waters, this is 45 degrees. Why the direction is to the right? Because this is in the northern hemisphere. Northern hemisphere, your water mass is affected by the Coriolis force. So, even if you have a wind direction in this, so the current will not follow the wind direction, but it will be deflected to the right by an angle of 45 degrees. So, down below this water, I think the maximum depth of influence is 100 meters. So, this depth you can write as 100 meters. So, these vectors are decreasing because of the shear of the various layers of water. So, this is less affected by wind, etc. Down below it is going in the opposite direction. So, movement reversed. At base of wind driven surface current. So, this is your base and the direction is reversed. Now, if you want to study the Ekman spiral, you can do laboratory tests. So, can be produced in lab. Using rotating models. Now, this is also observed in the atmosphere. But it is difficult to measure in oceans. Possible to observe certain effects. Effects produced from Ekman spiral. So, in the open ocean, you will hardly see the Ekman spiral, which is difficult to observe, but you can make out that it is existing over there because of the existence of some kind of effects, which I will tell you now. Now, as a result of this Ekman spiral, what we are getting is a wind induced current, or rather a wind induced water transport. There is a mass transport of the water, and this play an important role in surface currents or surface ocean circulation. So, surface currents are largely created by winds, and the depth of influence is 100 meters, and there you will find the direction to be reversed. What is the effect of this Coriolis force? Coriolis force also gives rise to a current that is called geostrophic current. So, this is caused by rotation. Earth's rotation. The Ekman current is caused by wind. Geostrophic current is caused by rotation. So, now if your wind is going in a closed loop, what will be the direction of current? Say this is called a wind gyre. This you take in the northern hemisphere. Say a wind gyre has been formed in the northern hemisphere. So, in this direction, what is the direction of net water transport? You write surface current is there, your net water transport will be perpendicular to the direction of wind. So, this I have not written, you mark in this diagram. So, this will be 90 degrees. This is net water transport. That is the resultant of all these vectors in your Ekman spiral. Vectors from the surface to vector that is down below 100 meters. You take the resultant, it will go in this direction, 90 degrees to the direction of the surface wind, right? Whereas your surface current is only 45 degrees to the wind, but this is only in deep waters, and in shallow waters this will be 15 degrees. So, mechanics are somewhat a little bit different. Now, what I was talking about is the other one, that is the wind gyre. So, what should be the direction of the net water movement? So, obviously, this will be your net water movement will be perpendicular to the direction of the wind. So, it will come in this direction. Now, this gyre is a closed loop. Again, net water transport that is coming from this gyre will be coming in this direction. So, in which direction all the water is going? So, all your water is collecting towards the center. So, this is an example of a wind gyre. In northern hemisphere. So, prevailing winds. So, net water transport is towards the center of the gyre. So, very interesting. Huh? So, the water surface is not as flat as you see. So, prevailing winds tend to move surface water. Tend to move surface waters. Now, it will move only the least dense water. Surface water is least dense, that is the density is minimum. If you go deeper down, then the water increases in density. So, the least dense waters towards center of ocean or center of the gyre that I have told. Center of ocean circulation. So, this is what is happening. Now, as a result of this leads to a low hill of water. So, a water mass has accumulated at the center of the gyre. So, low hill of water has been created, less dense. At the center of wind gyre. Now, highest elevation you write is 2.4 meters. So, that is exceeding a man's height. Highest elevation is 2.4 meters. This is above arbitrary level. And this occurs in North Pacific of Japan. This is of course the highest elevation. The smaller gyres you will have lesser, and the lowest he has given as lowest elevation occur near Antarctic. Now, highest elevation occurs as in this coast of Japan, So you write highest elevation occurs near western ocean boundaries. So Japan is towards the west of the Pacific. So boundary is land. Now if you look at the mechanics, you will find this low hill of water. So this gives us the direction of movement of the water particle. So this is a particle of, so this is acted upon by a gravity force. G is acting downwards on the particle, and your centrifugal, because of the rotation of the earth, your centrifugal force will act towards the center. And if you take the resultant, you will get a direction like this. So the path of the particle will be somewhat in this manner. So that is your geostrophic current. Now because of the wind driven current, you have two aspects which are caused by wind. One is called upwelling. As opposed to this, you have sinking or downwelling. So these are caused by wind induced vertical water movement. So this is the dynamics of your upwelling. Say you have a mass of land on the right hand side, say a beach or a shore. So this is your land mass. Now your wind is going in this direction. Now you are taking in the northern hemisphere, so the deflection of the water will be towards the right. That is your surface waters. So net water movement will be towards the right in the northern hemisphere. Now if you look at the cross section, you will find that the situation is like this. So this is your land cross section. Your wind is coming in this direction, and at the sea surface your net water transport is going towards the right. So what is happening to the water down below this? So you are moving your surface waters to the right. Obviously you are generating some kind of a vacuum, and your bottom waters are going to come up to the surface because of this wind. So this is the phenomena which is called This is your sea surface. So this phenomena is called upwelling. So in this, actually the bottom waters are driven to the surface because of displacement of the surface water, that is, you are moving surface waters away from the shore, you are causing some kind of a vacuum and your bottom waters are coming up. So this phenomena is called upwelling, and opposite of this is called sinking. Now both these phenomena are taking place in the northern hemisphere. So this is your land mass. Now you tell me which direction the water will go. Your wind is going, say, in the reverse direction, from bottom to top. Say this is the direction of wind, then what will happen? So northern hemisphere, your net water transport will be towards the right. So water is going to move towards the coast. So this is your water. Sorry, this is written in the land portion. Now if you look at a cross section of the shore, you will find this is your land. So wind is going away or blowing in the opposite direction, but your net water transport is towards the land. So water will tend to pile up towards the land. So the direction of flow will be towards the beach or shore, and this water from the surface is going to push the other waters down. So like this. See, this is your envelope. So this is your sea surface. So it is behaving in the opposite direction. So this is called sinking, or sometimes in some books you will find this is called downwelling. So which one is favorable, upwelling or downwelling? Though in the previous case, that is in the upwelling case, you will find the bottom waters are coming to the surface. So obviously this is good for the aquatic animals or fishes. So at the bottom there is food is going to circulate. So fishes cannot come up to the surface, have their own feed and then go back. In this case the opposite is happening actually. Now this upwelling actually takes place to a large extent in the Peru coast. Where you can have fishing grounds. So oceanography is also required for fisheries. That is one of the reasons. So with this we finish this physical oceanography. Now the next is we have some time. I think I have to go because of this clock set by these people, So I could have given you off, but let us talk for a few minutes. Now, physical aspects of water. Now, water has, what is the heat retention capacity of water? So, first is number one, of course, is pressure. Water has pressure. Number two is what? Heat. Or rather you write heat capacity. So, this is called thermal property. There is a thermal property of water which we will discuss. Now, heat and thermal property are governed by temperature. So, you can use this temperature to your own use. So, heat causes rise of temperature. The last property that is affecting all of us is number 3, you write salinity. Now, this salinity influences conductivity in the water. Rather, you can write ionization of water particles. After salinity is what? The last one, density. So, water has seawater. Basically, these 4 properties are important. That is pressure, heat, salinity and density. So, we will study this in our next class. So, all these particularly 1 and 4, they affect, of course, salinity is also influences density. These are affect what is called ocean circulation, currents. Ocean circulation is caused by these parameters also. So, next class we will see how this influences your current. Okay, thank you.